In today's session, we will cover how we can extract average integrated variables in a location inside the fluid domain. The model that will be used to demonstrate the process is a simple mixing elbow with two inlets and one outlet, as shown here. The goal will be basically to extract some averaged physical quantities like temperature, pressure, velocity in the location where the two incoming flows are mixing. Okay, let's now jump into SimLab. As we can see here, we have the volume-est mixing elbow model assigned with a water material. And if we take a look at the solution tree, where I have already defined the physics of the problem, we can see the boundary conditions like the small inlet at the bottom, the outlet at the top, and the large inlet at the left. Okay, now that we have taken a quick look at the model, let's just run it and move on with the post-processing. For this session, we will choose the flow post-processing option because it gives us more advanced CFD post-processing tools. Here we have the post-processing window. In here, we could make all kind of cool visualizations, but today I want to focus on extracting average integrated data in a region inside our domain. This is something that is often required when we are doing a simulation, since we usually want to extract average values of our physical variables in some critical regions of our model. For example, in an HVAC application, we would probably want to extract integrated average values of mass flux, pressure, or velocity for the various vents of the system. In each application, the critical regions inside the fluid domain might be different, but in all of them, we are usually interested in this kind of averaged quantitative data. In the case of the mixing elbow here, we would probably be interested to see what are the average values of our physical quantities exactly where the two incoming flows are mixing. One of the ways that we can compute these average values is with the cutting plane and the integration tool here in the post window. So what we have to do first is to create a cutting plane exactly at the region of our interest, in this case the region where the two flows are mixing. So I will press on the cutting plane, and then move it on the y minus 0.05. And then just press OK. This creates the cutting plane. And if I make the volume transparent, I can see that it is located very close to the mixing region. Now the next step is to just click on the integration tool, select the cutting plane from the tree, and then simply press calculate. As we can see, this gives us an average value for several variables like pressure, velocity, or temperature. So the process that we have just shown can give us the average quantities that we are usually interested in, but it has two main disadvantages. The first one is that it may have a low accuracy. And this is because the cutting plane is interpolating the physical variables from the surrounding nodes. So in a case where we have a coarse mesh, the interpolation at the cutting plane will not be very accurate, and therefore the averaged values computed out of it will also not be very accurate. The second disadvantage is that we cannot really track these values in time. Having a report of these values at every time step is crucial, of course, in a transient simulation, but it can also be useful for a steady-state simulation because we can deduce whether the physical variable is fully converged at a specific value. So, what can we do to avoid these disadvantages? What we could do is to make sure to create a surface monitor for any internal surface of the domain that we are interested in before we run the simulation. So let's go ahead and see how we can do this. I will go back to my model here. I will delete the volume S. And I will make sure to break the body in the regions that I want. In this case, I want to break it with a plane at y equals to minus 0.05 to create a surface close to the mixing region of the elbow, similar to what I did in the post ribbon with a cutting plane. As we can see, this gives us two volumes now. I will then just use the remesh option to remesh my surfaces with a better mesh. And then I will reproduce my volume mesh with the usual process. Okay, after creating the volume mesh, we can do also a section cut and see how the mesh looks inside. As we can see, we now have an interface between the two volumes, and the mesh nodes are lying exactly on that face. After creating an interface exactly where I want to measure my averaged quantities, I will assign a surface output to it and name it however I want. Now I will just save this new database and then rerun the simulation. After the simulation has finished, I will go directly to AccuProbe, which is our plotting utility, I will insert a log file of the AccuSolve simulation, and as you can see, we now have access in AccuProbe for the integrated averaged values on this monitor surface. Let's see, for example, the average integrated value for the pressure. Now, if I bring back the post session from the previous simulation, we can see that there is a difference between the values of pressure computed by the post-integration tool and the value computed by AccuProbe. As I explained previously, this happens because the value computed by the cutting plane and the integration tool has lower accuracy because the cutting plane interpolates the solution from the surrounding nodes in the mesh, while the value that is computed by AccuProbe is actually computed with mesh nodes lying exactly at the interface. Besides pressure, we can also compare other physical variables like temperature, or velocity. In this case, we only have a slight difference from the post-integration tool, but in other cases where the mesh might be more coarse, for example, the difference will be larger. Finally, as we can notice here, we have tracking in time for the averaged quantities, which can be very important, especially for transient applications. So to recap, today we have seen two ways with which we can compute averaged physical variables inside our fluid domain. The first, and actually the most recommended one, is to create surface outputs before we run our simulation, exactly at the regions where we need them. And the second way, in case, for example, we forgot to create a surface output, is to use the cutting plane and the integration tool inside the flow post-processing window of SimLab.